We have already learned about the Cartesian plane, and in this video we shall be learning about how it can be used to visualize relationships between variables in the form of graphs. The two axes named x and y can be used to represent two variables, x and y. The Cartesian plane can now be used to visualize relationships between x and y. The simplest of relation between x and y is y equals x, where whatever the value of x, y just simply equals it. What that means is if x equals 1, then y equals 1. If x equals 2, then y equals 2 as well. With no limits being set, we can put any numerical value for x into the relation and obtain the corresponding y value. With so many possible numbers, it is good to build a table of x and y values to get a collection of pairs of x and corresponding y data. To do that, construct a simple table with 2 rows and a few columns. Place the letters of the variables x and y into the first column. Now decide upon the values of x that you wish to supply into the relation and write them down on the row for x. In this example, I have chosen to supply x equals negative 12, negative 8, negative 4, 0, 4, 8, and 12. And this is because those values of x are available on the Cartesian grid on the left. Next, take each of those x values and put it into the relation to obtain the corresponding y values. The relation stated here is a simple one where y just simply takes the value that x has. When we put x equals to negative 12, y equals negative 12. When x equals negative 8, y equals negative 8, and so on. But I have chosen not to evaluate for x equals to negative 4 and 8, though the answer is obvious. You shall see why later. With that done, now we have 5 ordered pairs, which basically forms 5 coordinates. One by one, plot those coordinates on the Cartesian plane on the left. Negative 12, negative 12, negative 8, negative 8, 0, 0, 4, 4, and 12, 12. When plotted, we can easily see that the points seem to form a straight line. If we attempt to connect the points in sequence, a straight line graph is obtained that passes through the origin. And once we have done that, we have successfully illustrated this relation as a graph. To check if our graph is indeed supposed to be a straight line, we supply a new value of x into the relation and into our graph. We put x equals to 5, and the relation says that y should be 5. That's obvious. We put x equals to 5 into the graph, and it says y is indeed 5. So therefore, our graph is correctly representing the relation. How about those missing values of y that we chose not to evaluate? With the graph now representing the relation perfectly and accurately, we can use the graph to find the values of y. From the graph, when x equals negative 4, the value of y is negative 4. The coordinate of that point on the line is thus negative 4, negative 4. When x equals to 8, the value of y equals 8. The coordinate of that point on the line is thus 8, 8. We can then enter the values into the table with confidence. What we have learned now is that we can draw graphs on the Cartesian plane to represent relations between variables, in this case 2 variables x and y. The significance of this line representing this relation is that every point on the line will satisfy the relation. In other words, the graph connects every point that satisfies the relation. This point on the line will satisfy the relation, but these points not on the line will not. Let's upgrade the relation to something slightly more complicated, y equals 1.5x minus 3. Once again, we build a table with x values that we wish to supply into the relation and evaluate the corresponding y values. Substituting x equals negative 12 into the relation results in y equals negative 21. Proceeding with other x values results in these corresponding y values, and we obtain 6 coordinates. I have chosen not to evaluate x equals to 4. Plotting the known coordinates one by one on the same Cartesian plane on the left and connecting them the way we have done before results in another straight line. Do take note that I have not plotted these points because the scale on our Cartesian grid does not accommodate them. There is one value of y that we need to find, and that is for x equals to 4. We can now obtain the value of the relation when x equals to 4 from the graph instead of substituting x equals to 4 into the relation. And this is because we are confident that the straight line we have drawn accurately illustrates or describes the relation. From the graph when x equals to 4, y equals 3. And checking with the relation by substituting x equals 4 into it would give us the same y value of 3 as well, thus confirming that we have indeed correctly drawn the graph of this relation. The two graphs we have drawn are straight lines. The relation that results in a straight line graph is called a linear one. Therefore, these two relations are linear relations. There is, however, one exception, which is the vertical line, and we shall see that in another video. For now, for comparison, we shall take a look at another example, this time of a nonlinear relation. We have y equals x squared minus 4. A table is drawn, values of x selected and entered, values of y obtained from the relation, and one left out to be obtained from the graph instead. These coordinates are then plotted on the grid. If we attempt to connect the points one by one in sequence, we do not get a straight line through them, thereby proving that this relation is definitely nonlinear. The best graph drawn through those points will then have to be a curve, and when drawn properly, a U-shaped graph is obtained. Now that we are confident that the graph drawn accurately describes the relation, we can use it to find the missing y value. From the graph, when x equals 3, y equals 5. You can verify that using the relation as well by substituting x equals to 3 into it, and yes, y does equal 5. Summary of what you have learned. Point number 1. A two-dimensional Cartesian plane can be used to illustrate a relation between two variables in the form of a graph. Point number 2. It is good to come up with a simple table of x and y values to derive coordinates for the graph. Point number 3. The scale you have used for your Cartesian plane or grid determines if all the obtained coordinates can be plotted. If it is necessary to plot each and every point, then rescale your grid to accommodate them. Point number 4. A relation that results in a straight line on the Cartesian plane is called a linear relation, with exception for the vertical line. Point number 5. When the graph drawn is accurate, we can then use the graph to obtain the y when x is given, or obtain x when y is given without the need of substituting and evaluating from the relation. And this is because every point connected by the graph will satisfy the relation it represents. And finally, a note. From the next video onwards, the term relation with variables in it will be called equations, and the Cartesian plane will be simply referred to as the grid.